Welcome back to a tutorial, and in this video, as you can see, we're going to learn about how to minimize digital functions using a Karnaugh map. Okay, so let's say we have a function, okay, which is given by, well, f. Okay, I'm just going to write it here. F equals to it's given by pi m of 2. There we go, 2, 8, 9, and then we got, well, 10, 11, okay, and then 12, and finally 14. Okay, so what we're supposed to do is we have this function and we have to, well, reduce it using a K-map. So our problem statement reads minimize f equals to pi of m, this function over here. All right, we got to basically minimize it and implement the reduced expression in universal logic. So what we got to do is that we just need to reduce this function, okay, using a K-map, of course, and whatever the reduced expression would be, we got to implement it using, implement the circuit, okay, using the universal logic gates. Okay, so as you can see, as this function it indicates, here we have this symbol of pi over here. Okay, now this pi symbol indicates that it is a POS function, okay, that is the product of sums. Okay, so now whenever we have a product of sums expression, we know that in a Karnaugh map, all these variables, or rather these elements that are basically present in the function, would be filled up in the Karnaugh map with the symbol 0. Okay, done. Okay, and furthermore, we also know that whenever we're basically taking the reduced expressions, or rather just writing the expressions of each of the cells, then we must always keep in mind that whenever we're dealing with POS functions, then a 0 is regarded as a non-barred quantity, whereas if it's let's say a variable is there as a, if it's in the POS form, we would represent it using 0, but if it's a bar, it would be represented as 1. Okay, so 1 always indicates in inverted quantity, whereas a 0 indicates a non-inverted quantity when it comes to POS functions. You should always keep that in mind. Okay, so let's just go forward and, well, draw our K-map. Okay, so we're basically, gonna draw our K-map over here. Let's say, okay, so here we can see that we are gonna need a big K-map, but the question is, how many cells do we use in the K-map? Okay, we can get to see the if we just take a look at the function over here again, we can see that the highest value of the element over here is 14. Which means that if we take, we will basically, require at least, or rather a maximum of 16 cells. So which means we will be needing a 4x4 K-map. Okay, so we're going to need a 4x4 K-map. All right, so let's just make it up. Okay, so this means that it's going to have, 4 columns and 4 rows. So let me just draw the columns first. 1, that's 2. And there you go, 4 columns, and then we're gonna need 4 rows also. So we have, that's 1 row here, that's 2, and there you go, we got 4 rows and 4 columns. Okay, and now let's just number it up. So we got 0 0 0 1 1 0 and 1 1. Over here the same thing would follow for the rows. Okay, there you go. And finally we can see that in this Karnaugh map, which is about, contains 16 cells, okay, then it should be numbered from within also. So we have 0 over here, 1, 2, and then 3. So this is the way how the Karnaugh maps should be numbered, as I have shown you in the previous tutorials. So 4, 5, this is 6, and this one's 7, and then you go back to the lowest one, okay, and then you have 8, 9, 10, and then 11 over here, and then you got 12, 13, this one's 14, sorry, there you go, 14, and this one's 15. So 0 to 15, that's 16 cells in total in this K-map. Okay, and also we can get to see, if we just take a look at the function once again, we know that it's a POS function and we're requiring 16 cells. So which means that if we just take a look at the the binary data, I mean the binary numbers over here, then we'll see that for the columns we need at least 2 variables to specify them, as well as for the rows. So let's just take the variables. So in total we are going to need 2 variables for the columns and 2 variables for the rows. Okay, so let's just take 2 variables. Let's say AB for the rows and the other 2 variables CD for the columns. Okay, so now in total we are having a particular cell, okay, is represented, the binary code of a particular cell is basically represented by a combination of 4 variables, that is A, B, C, and D. Okay, so that's the Karnaugh map. Okay, now we're going to fill it up. So we can see that 2, 8, 9 is contained in the function, so we're just going to fill up the 2, 8, and 9. All the elements over here. These are the numbers of various cells. We're just going to fill it up by 0. Okay, so 2, 8, 9. So we're going to put 0 in place of 2, and then 8 and 9. There you go. And again, let's just change the color for the moment. That just make it easier to see. Okay, so that's 0 over here. All right, there you go. And then again we got 10, 11, 12, and 14. Alright, so let's just fill it up. 10, 11, and then you got 12 and then 14. Okay, now is the time to make the groups. Now we can, as you'll know, that the Karnaugh map is foldable. Okay, it can be folded both ways. Alright, it can be folded from top to bottom, upside down, as well as it can be folded sideways. So we're just taking, so we can basically see that the cell number 2 is adjacent to the cell number 10, so we can basically group them up together. So there you go. Now we have one of the groups. Okay, let's change the color once again, and then we can have another group over here consisting of starting from the cell 8 to cell 10, that consists of 4 zeros in a row. So this entire row over here in green is another such group. And then we can use some other color. Let's see. Okay, let's just use this color over here. Okay, then we can get another group. So if we just try and fold the Karnaugh map sideways once again, then we can see that the cells 12 and 8, okay, come adjacent to the cells 10 and 14. So once again we have another group over here consisting of another quad. So we have 2 quads, okay, and a single duplet. Okay, so let's just write the the expressions for each of the groups over here. So let's just take the pink circled one, that's cell 2 and the combination of cell 2 and 10 as group 1. So for group 1, okay, the expressions that we can get would be written something like, let's just check them out over here. So 2 consists of, remember that this is a POS expression, so it's just a product of the sums. Okay, so we got to find the sums for each of the cells. So we got this is 0, 0 and 0, 1, which means we can get A bar, B bar, okay, and then we'll get A, B, C bar, and D for the cell number 2. So that'll be A, B, okay, and then C bar and D. Okay, there you go. So always remember that whenever you're just using POS expressions to find out the minimal expression with the Karnaugh maps, then always remember that whenever there's a zero quantity always represents a non-complemented value. So a 0 will always represent A, okay, whereas if you have a 1, then it'll represent a complemented quantity. Okay, so if we're basically trying to express A bar in terms of POS logic, then it'll always be represented by 1. Okay, whereas A would be represented by 0. That's why whenever we can see that here we have 0, 0. That means A and B are both zeros. Okay, C is 1 for the cell number 2, and D is a 0 again. So since A, B, and D are all zeros, so you can see that in this particular expression, none of them has a complementary bar sign above their heads, so which means that they are non-complementary values in terms of POS logic, whereas C having the value of 1 over here is a complementary value. So that's how POS, expressions are basically framed in POS logic. So this particular thing would be multiplied with the address of another, the expression of the other cell, that's cell number 10 over here. So here we got, here A is 1, so we can put it as, A bar, and then B is 0, so B, plus that of, the column address reads 1 0, so which means that C is again a complementary quantity and D is non-complementary. Okay, so now we have this particular expression, okay, that's the product of the sums, okay, for the group 1, and now we need to reduce it to as low a value as possible so that it'll make it'll just shorten our labor and complexity involved in carrying out the bigger calculations. So if we just try and reduce this one, you always need to spot the common factor. So you can see that B, C bar, and D are common in both these expressions. Okay, so you just extract them out, and whatever remains over here, you can see that A and A bar are both complementary quantities. So if you just I'm just jumping the steps over here, but if you would care to take all the pain to multiply these two quantities and solve them using De Morgan's theorems, then you'll find that the ultimate solution to this multiplication would result in B, C bar, and D. So it's quite a tricky way to shorten all your effort if you just take a look at whatever are the common terms, and the rest will be all available in complementary values. So one would, here you can see that you have A and A bar. Okay, so if you just multiply them, A and A bar, they'll just cancel out together. If you just carry out the calculations in detail, you'll find that. Okay, so for group 1 we have this result, and then now if we just go to the green group, that's group number 2 over here, then we can see that there's go. Okay, group number 2. For group number 2, we have 4 cells over here. So if I just write them down together, then we got 1 0 and 0 0, which means that we got A bar B plus that of C D. Okay, and then we can obviously take a look over here that fine. So here you can see that A bar B is just the common one for all the cells, and then for the cell number 9 we got the other two as well. Yeah, C and D bar. Okay, C plus D bar, and then again A bar B plus for cell number 11 we got C bar D bar both. Okay, and again for that of cell number 10 we got C bar and D. Okay, so we got A bar B plus that of C bar plus D. Okay, now you can see that in entire in all of the 4 expressions over here, you again have let's just take 2 at a time. So if you just take these 2 and the other 2 together, then we can see for the first 2 we got A bar B C common. Okay, A bar B C common. And then again for the last 2 we got the common terms as A bar B and C bar. Okay, A bar B and C bar. Alright, and now whatever we can see over here, we can get to see that we have now we can get to multiply them once again. So we can get to see that we have A bar B common in both of them. So if you just go forward and simplify it even further, we're going to get A bar B as the result of the the reduction involved. Finally, if you take a look at the last and third group over here, that's the other quad. Okay, so I'm just going to write it down as group 3. So for group 3 you can see that we have the cells we're gonna have the cells 12, 8, 14 and 10. Okay, so if I write down the necessary expressions for each of the cells of group 3, then it'll be something like A bar plus B bar plus that of C plus D. Okay, let me just take a look once again. Okay, and then we got the other term, which is which reads something like A bar plus B bar plus C bar, and then again we got another D, and then again we have the third term for the other cell that reads yeah, a bar plus b plus c plus d once again. And finally we got, well, okay, I'll just write it below. We got, well, a bar plus b, right, plus c bar plus d. Okay, that is of course cell number 10. Okay, a bar b plus c bar d. Okay, so now that we got all the the expressions for the third group over here, now it's the time to reduce them together. So let's just spot the common ones. Now we can see here that a bar, let's just take the first two and the last two again, like the previous one. Now we can see over here that a bar, b bar and d are common in the first two, so let's just take them out. Okay, so we're gonna take them out over here, and the rest you can see that c and c bar are just complementary values. They'll just cancel out together. Okay, and for the second two we can see that, well, we have a bar, b and d once again common, so let's just take that out together. Okay, a bar, b and d common, and now we can see apart from them we have the c and c bar as the complementary values, which will just cancel again. And now again over here we repeat the same thing, and finally we come to the conclusion that we have a bar and d common in both of them, so we just take that out. Okay, so ultimately we're gonna have, well, a bar plus d as the reduced expression for group 3. So the resultant reduced expression which we are searching for the function f, okay, it's gonna be the product of the reduced expressions of group 1, group 2, and of course group 3. So if I just write them up together over here, okay, if I just write them together, so the resultant expression, so this is the f, I'm just gonna write it as f resultant. That's gonna be it's just gonna be the product of all the results of all the groups. But wait a minute, let's just put it as, well, something like f min. Okay, so that just is more accurate, so I'm just gonna put it something like that. So okay, just give me a second there. So f min, so that's the reduced expression, and that's going to be the product of we can see here b c bar d, that's the result of group 1, b plus c bar plus d. There you go. And then we got the result of group 3, that is a bar plus d. And then finally we got, well, the result of group 2, that is a bar plus b. Okay, so there you go. That's our reduced expression that is just being generated as a result of solving this Karnaugh map. And now if we would just peek our minds a little deeper into the result which we got over here. Okay, so the job left for us is only to implement this in a circuit. Okay, so we should always keep in mind that since we have been told in the problem statement to design the circuit using universal logic, so we should always keep in mind that the universal gates are the NAND and the NOR gates. Okay, so the question is, with what type of gate do we design the circuit? Alright, so since it's a POS, since the the original expression was in the POS form, and the result that we have over here is also in the POS form, so it's always easier to implement this particular POS expression, any type of POS expression, using a NOR gate. Okay, so we'll basically be trying to implement that with a NOR gate over here. Alright, so in that case, let's just convert this result in terms of NOR logic. So I'm just going to write that down once again over here. Okay, so that's b c bar d, and then again a bar plus d, and then a bar plus b. And then what you do is you just add 2 bars, okay, so that bar and bar would just cancel each other. Okay. Alright, so now whenever you have this, now you can just take the inner bar and this expression, okay, and just apply De Morgan's theorem. Now, according to De Morgan's theorems, okay, you'll get it's something like this, as you'll have the top bar and all of these quantities would just divide together, and all of them will be just become, you know, inverted quantities collectively. So you'll have B, C bar, and D, okay, bar plus that of A bar, D. All right, and then you'll have A bar plus B bar. Okay, so this is what you get whenever you apply De Morgan's theorem to such a kind of expression. Now you can see that, well, as NOR is just the complementary of the addition, or rather the ORing of you know, the respective inputs. So you can see over here easily that we have the entire expression, that's the minimized expression, mapped up in the NOR logic. So if we just look at, or rather if we just take NOR gates together, okay, I'll just use the other color over here, okay, that's better. So if we'll need basically 3 NOR gates, okay, so there you go, that's NOR gate number 1, that's 2, and this one's 3. Okay, so now we are basically gonna have, well, 2 inputs for the first NOR gate would have, well, 3 inputs, okay, and then the other one would have 2. Okay, the other 2, that is, will have 2 each. And then finally we can see we'll have the input variables as well. B, this one would be C bar, and this is D. And then again for the other one we'll have, well, A bar and then D. And for the next one we'll have, or rather we can just, well, join the A bars just together and the D's together also. So let's just not write them up once again. Okay, we can just, well, join them up together so that it's just, well, easier. All right, so I'm just going to join them up together over here. Just hold on a second. Okay, so we're going to join the D's together so that we have a common input, and similarly we can join the A bar together so that we have another common input over here. The only input that is extra would be B, and we can also join B together since we have one already. Okay, so now that just makes up our circuit, and finally the entire output, that is these quantities, would just be needed to pass through another NOR gate so that they could be just, well, added up and their complement could be taken. Okay, so we are gonna basically have another you know, NOR gate over here. Okay, having 3 inputs, and finally over here whatever output we get, that is exactly gonna be the resultant expression which we have right over here. Okay, so that's all from this tutorial. Okay, hope you've enjoyed this one, and I'll be seeing you next in the other tutorial on the K-maps, where I'll be showing you what you have to do whenever you have don't care conditions. Okay, so till then it's just gonna be a wrap up at this point, and keep watching, and you don't forget to, you know, go forward and watch our next tutorials. Thank you.